and welcome back to another lecture of Statistics 479 Time Series Analysis. Last lecture, we looked at the ARMA process. We looked at how to estimate coefficients, and we started talking about forecasting, but we didn't really get past the mathematical nuances of forecasting. In this lecture, we're going to get into real forecasting with real data. So what we have to talk about is how to do forecasting with real data, because real data is not infinite, something that we don't often like to talk about. But in fact, you do not have infinite data, you only have a finite amount, and you have to figure out how to do forecasting for a finite amount of data. We're also going to take a small diversion and talk about backcasting, because sometimes you don't want to predict forward, you want to predict backwards. Lastly, we're going to take some time today and look at a bit of R code and some real data, because we've been doing a lot of studying so far of the mathematics, but it's really good to get a sense of how this works for real data. So we're going to jump into the notes. I'll see you there. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to continue our discussion of forecasting for the ARMA process. We started it in the last lecture after doing estimation, and we talked about some mathematical ways to understand forecasting. Specifically, we pretended that our data extends infinitely into the past. But it doesn't, right? We don't have infinite data to work with. We have a finite amount of data because that's typically how data works. So what we have to do is look a little bit closer at our forecast, because right now we're sort of in this ideal math world of forecasting. We have to forecast in the real world. That's what we're going to do today. So let's jump into the notes and see what we get. All right, so what I wanted to do was just start by recalling some of the notation that we used in the last lecture so that we're on the same page. So first of all, we'll just say this is forecasting for ARMA, PQ. Now, when we're doing forecasting for an ARMA process, right, first we need to note, well, what does the ARMA process look like? It is going to look like capital Phi B of xt is equal to capital theta B of wt. So we have our autoregressive piece, we have our moving average piece, and we're going to assume, of course, that this is causal and invertible, as usual. And furthermore, we had two different notations for forecast, for predictions, predictors, I guess. We had our h step ahead predictor, capital T plus h, which is the expected value of, well, just the time series process itself at time t plus h given the observed data capital T down to 1. And then we also had this notation of x tilde capital T plus h, which is going to be the expected value of xt plus h given the data and all the hypothetical data that would extend into the infinite past. Again, physically we don't have that. Mathematically, we can always think of our stationary process as extending infinitely in time in both directions. We want to use the past to predict the future. It's stationary, that's good. But the thing is that we don't typically have infinite data going all the way into the past. So we have to figure out what's going on here. So to speed ahead to what we did last time, we found a couple things. I guess what we found, there's all the good stuff, right? What we basically found is that there's a couple ways to look at the process. So I'll say from last time, what we had was this idea that, well, we can write xt or x tilde T plus H in its causal form, and it's going to look like mu, the mean of the process. Again, we can assume mu is 0, but if it's not 0, we can also adapt our equations for a non-zero mean. Now, what we're going to do is we're going to have our summation here, but we're starting at h. And we're taking psi j w capital T plus h minus j. So the point is that, as we noted last time, this is a tail sum from h to, I'll say 2 because h is not converging to infinity, so I shouldn't use an arrow there, right arrow. I should just say h to infinity. And we saw some properties at the end of the last lecture, most notably that in the limit, x tilde capital T plus h will just converge to the mean. That is, our prediction will, this is as h goes to infinity, I should say. So what that means is that our prediction far into the future is just the mean of the process. And again, this makes sense. I mean, you always think of stochastic process as like some stock market that's jumping up and down, but that's a random walk. In this case, we have a stationary process. Stationary process looks a lot like white noise. Okay, it's not white noise. There are autocorrelations, there's moving average pieces, but it's going to be fluctuations above and below some mean mu. So if we go really far into the future, our data in some sense no longer matters. We're just going to say, well, the best guess we got is the mean, whether it's 0 or whether it's mu or otherwise. Now, what I didn't do in the last lecture was I didn't talk about the convergence. So I think I mentioned briefly that this converges in probability, and I thought mathematically it would be nice to actually show that before we move on to the next section. This is kind of a standard trick to show convergence in probability. We're going to use something called Chebyshev's inequality, which is a really useful tool in probability theory and statistics when you're dealing with random variables, especially when you want to show convergence in probability, because it's all about the variance. Remember, Chebyshev's inequality, about the variance. Okay, so what are we doing? Well, what we want to do is we want to basically prove this convergence. Well, how do we do that? Well, converging in probability basically says that we want the probability that x tilde t plus h minus mu is greater than epsilon, and we want this thing to go to 0. So this is the probability that our random variable differs from the mean, the limit that we believe is there, by some amount epsilon. Epsilon, this is basically for any, I should put that in, any epsilon greater than 0. So for any epsilon greater than 0, as h goes to infinity, we want this thing to go to 0. How do we show it? Well, the first thing we note is we can use this definition here that the green arrow is pointing at, and if we subtract the mean, we find out that we're just looking at the probability that our tail sum, j from h to infinity, of psi j w capital T plus h minus j, we want to know what the probability that this thing remains bigger than epsilon. Now, we already said last time, intuitively, this thing can't be bigger than 0 in the limit as h goes to infinity, because we need, basically, if this was in a series sense, right, we need the tail sum to go to 0 so that the series converges. We know the series converges. We know that it converges, I think, absolutely. But what we need to do is we need to try to make it more precise in the case of random variables, because this isn't just a series with real values, real valued summands. It's a series with random variables. And what we can do is we can apply the Chebyshev inequality. And what that says is that this probability is bounded above by the variance of the thing in the probability statement, which is the sum j from, not 0, j from h to infinity of psi j, wt plus h minus j, and this is divided by epsilon squared. Now, the thing in the the numerator that is the variance, well, this is just the variance of a sum of a bunch of white noise pieces, I guess white noise terms. And what we end up with is, well, we're going to get an epsilon to the minus 2 here. And then we're going to have, well, maybe I won't write it like that. I'm going to write sigma squared, epsilon squared in the denominator. And then we're going to get the sum h from, not h, j from h to infinity of psi j squared. And we already know that this has to go to 0 as h goes to infinity because, well, a couple things. Sigma squared over epsilon squared is fixed. That's not changing. We're not taking epsilon to 0. This isn't one of those epsilon delta type things where we take epsilon to 0. We just have epsilon as any fixed positive number. This will work. And the summation j from h, well, the summation from 1 to infinity of psi j squared is finite. And if a summation, an infinite summation is finite, that means the tail sum has to go to 0 as you take h to infinity. So that is where we kind of formalize this a little bit better. And we don't just say, yeah, we just kind of go to the mean as you try to predict h further and further and h steps further and further into the future. But what it does tell us, right, is that now we actually have convergence in probability. Now, we could try to do, I think, convergence almost surely. It's a stronger result. I'm not actually sure if it would hold. If you want to try it at home and you really like probability theory, you can give it a shot. I would probably look at the Borel-Cantelli lemmas because those are the only tools that I always think about when I think about proving almost sure convergence of something. But we're not going to get into that in this course. We just want to basically try to be a little bit more rigorous about the result. And there's one other thing that we also noted from last time. So this is bullet point statement 1. And the other bulleted statement is that our mean squared prediction error, t plus ht, is equal to sigma squared, the sum. And now it's just the sum j from 0 to h minus 1 of psi j squared. So it's kind of like the opposite sum, right? Our the sum we had in the proof is from h to infinity. This one is j from 0 to h minus 1. And we know that in the limit, this thing will converge. And this is just a bunch of real numbers, so we don't have to talk about probabilistic convergence. In this case, it's just going to converge to j from 0 to infinity of psi j squared. And we know that's finite and equal to the variance of the process xt for whatever t you want. It's stationary. All the variances are the same. All right, so that's kind of the recap of where we're at. Now, all right, so what do we do with the fact that we're working with x tilde and not x hat? So this is the section called truncating the infinite past. Seems like a good title for a short story or something, if anyone's a fiction writer out there. Anyway, yeah, so what are we doing? Well, what we're going to do is we're going to note that, so there's two approaches. One is that if the data size t is small, we can just solve a linear system of equations as noted, I think, a lecture or two ago. But if t is large, we're not going to be able to do that, and we're going to have to go forward iteratively. So now what we're going to do is we're going to use the invertible representation, because remember last time I said there's two different ways we can write a process. We had the causal way of writing the process as a linear causal process. That's at the top of the screen here. This is x tilde, right? I'll put that in here as a causal representation. But what we also have, if we come down here, is the not the causal, but the invertible. So if we consider the invertible representation, then what we have is we have that x tilde t plus h is going to be, well, two things, right? First of all, if we have terms that lie in j from 1 to infinity, or not 1 to infinity, 1 to h minus 1, these are the things that lie outside of our data set in the future, I should say. These lie in the future of our data set. We have our pi I and our x tilde t and t plus h minus j. So we said this last time, we're going to predict based on the previous, we're going to predict the h guy, the h step ahead estimator based on the previous estimators, or sorry, predictors, I should say. Strictly speaking, we're doing prediction, not estimation. So what I meant to say was the h step ahead prediction is based on the h minus first and h minus second and so on predictions. And it's also based on the the actual data set, which is j from h to infinity, because we're still pretending that we have infinite data, and we get something that looks like this. Right, we got this from looking at the invertible representation and then taking the expected value. Remember, the invertible representation is that white noise, Wt, is an infinite sum of x's, whereas the causal representation is xt, the process, is an infinite sum of white noise. There are two different ways to write it. And you can think of it in a sense that the causal representation is like an infinite moving average process, and the invertible representation is like an infinite autoregressive process. When you have an ARMA model, you have to account for both pieces there. Anyway, so we can also, so I should say, let's see, I kind of want to write these on top of each other. No, we'll just write on the next line. I'll say also, given ARMA coefficients, phi 1 through phi p and theta 1 through theta q, right? We're going to pretend that we just know what they are. Of course, we don't actually know what they are yet. I mean, we'd have to estimate them from the data, but whatever. We would pretend we know what they are. Then what I can do is I can write x tilde t plus h. Well, I can just write this as the, trying to think if I should explain this slightly better or if this makes sense. I'm going to write it all out, and then I'll just tell you where this came from in case it doesn't make sense where it came from. Why I'm writing an ARMA process with a bunch of x tildes. So first, I'm just going to write this out. We have the ARMA piece, or the AR piece. We have the MA piece as usual, which is going to look like theta j. Now I'm going to write W tilde t plus h minus j. And what this is, right? This comes from applying the expected value operator conditioned on the infinite data into the past, applying this to the ARMA model. So basically, what we did to get this equation here is we took the conditional expected value of each side, and we turned the terms x and w into x tilde and w tilde. Now, we defined w tilde last time, and I'm going to find it again so that we can properly define it this time. What in the world happened to w tilde? I know it's here somewhere. Ah, yes. There it is. We'll say where w tilde of, I guess it's a different notation, capital T plus h minus j is going to be the expected value of w t plus h minus j conditioned on, well, the data, just like I wrote in blue up above, into the infinite past. And this thing, as we saw last time, is going to take on two different values. If w lies, well, it's going to be wt plus h minus j. If, let's see if we can do this, j is equal to h or greater, j is greater than or equal to h, and it's going to be 0 if j is less than h. Because if j is less than h, then wt plus h minus j lies in the future of our data set. The expected value is 0. If j is greater than or equal to h, w lies within our data set, and the conditional expectation is just the w that we had in the first place. Because again of like this one-to-one correspondence between x's and w's. Now, okay, we kind of understand what this equation is. Where do we go from here? So similarly, well, no, we know what x tilde is, so we're good with that. And yes, we actually have another way of writing w tilde here, or w tilde. So w tilde t and little t. So this is, okay, slightly different notation, but I'm just using little t to make it easier to look at. Well, this is going to be two different things. We're going to have the moving average, or not the moving average, sorry, the autoregressive operator applied to x tilde, capital T, lowercase t, and then we're going to subtract the sum j from 1 to q of theta j w tilde t minus j. So this is, once again, it's basically the same thing I have up above. I'm just rearranging the terms slightly. All right, and we're back. And I realized I made one slight mistake here. When I introduced the invertible representation, what we were supposed to do is truncate it. And I didn't actually truncate it. I just wrote out the infinite sum going into the infinite past. But the idea here is that I can truncate this and, well, basically replace the infinity with a capital T plus h. And what we're doing now is we're basically saying, okay, I want to predict x tilde at time, I want to predict x at time t plus h given the first t observations. We wrote this as an infinite sum, but I don't have infinite data, so what do? Well, we just kind of scribble out the infinity and replace it with a t plus h. I guess this is technically supposed to be a t plus h minus 1, so that the smallest index on the x will be 1, right? Because t plus h minus t minus h plus 1 is just equal to 1. So yeah, that was a slight misstep on my part. The point is that we can just do that. And now when we take this and we plug it in to this equation, we can effectively just compute everything. I mean, it may not be straightforward, but if we if we use our data to predict the first H step aheads, I guess H minus one, like the first step, second step, third step, and so on, we can plug them into the ARMA part of this. And then we also have to compute these white noise pieces W. And the white noise pieces are computed down here based on, again, the past ARMA pieces and the past white noise pieces. So when we're doing forecasting for time series, it's really a step-by-step thing. We try to go H is equal to one step ahead. We use our data to try to figure out, well, one, what the data is itself and what the white noise pieces are. We have the data, we can figure out the white noise, we predict the next point. Now we have that one. Then we use the entire data set and our one step ahead prediction to do a two step ahead prediction, and so on. If it's not clear, we're going to do an example, and hopefully that will make things a little bit clearer, because yeah, it can be a little bit like, okay, yeah, that's it. It's like, well, wait, that's it? Yep, that's it. So let's do an example. In this case, we will take the simplest ARMA example I can do, which is the ARMA 1-1 process. And we're going to write that as xt plus 1 is equal to phi xt plus w t plus 1 plus theta wt. All right, so now we have our ARMA 1-1, and we can write down the one step ahead prediction. So the basically one step ahead prediction is, well, it's x tilde capital T t plus 1 is equal to phi x capital T plus theta w tilde t, I guess t. Yeah, because it's the teeth white noise piece. Effectively, we remove this and we estimate, or I feel like estimate is the wrong word. We predict this, and we already have this. So, right, we have the xt data point. The wt plus 1 lies sort of, I guess, ahead of our data set. That just becomes 0 when we take the expectation up above that I mentioned. And the wt here, when we take, or capital T, I should say, when we take the expected value of that, we just get w tilde t. Now, if we go for the H step ahead prediction, the H step ahead prediction is going to be continuing this onward, but the W's start to not matter anymore, because if we go back up to our definition here, any W after capital T and into the future to capital T plus 1 and so on, once we take the expected value, the W tilde just becomes 0. So we're only going to be looking at the AR piece here, which is going to look something like x tilde t plus h is going to be just phi times x t plus h minus 1. This is for h greater than or equal to 2. So all it's saying is that what are we going to do if we want to predict the future of our ARMA 1-1 process? Well, the first thing we do is we figure out what W tilde is, and we get xt, the actual observed, the final observed data point. Then, to get the next guy, we just take the previous estimate or prediction, multiply by phi. Then we multiply by phi again to get the next one, and the next one, multiply by phi again, and so on, just until we're satisfied, I guess, or until it converges to 0 and it's kind of boring. So in that case, it's kind of interesting. So basically, we need two things, which is xt and an estimate for wt, which is this w tilde tt. And that's all we need to do forecasting. Now, granted, the entire data set could be used to estimate phi and theta and things like that, like we talked about in the previous lecture using maximum likelihood. So we still want to have lots of data, right? But the point is, for forecasting, I guess we really only need that xt, and we still need to figure out what w is. So in that case, we're going to have to work a little bit harder. So then the question is, how to get w tilde tt. Okay, well, let's think about that for a second, right? We know, so we have, if we rearrange the above equation, where is it? If we rearrange our ARMA equation here, underlined in green, what we end up with is a wt plus 1 is equal to xt plus 1 minus phi x t minus theta wt. Now, if we take the conditional expected value of this, what we end up with is the idea that w tilde t plus 1 is equal to x t plus 1 minus phi xt minus theta w tilde t little t. All right, so what do we do? Well, so then we solve iteratively, starting with w tilde t0 equal to 0. So we start with white noise at time 0 being 0 and our observation x naught being 0. And then we just start computing. So we go in here and we say, okay, well, if I have that, then that means that what? W tilde t with a 1 is going to be x0, no, x1, sorry. x1 minus 0 minus 0. Okay, so that's kind of boring, but we're done, right? We got that. Okay, so we know that the first white noise piece is just the first observation. The second white noise piece, well, what's that going to be? In that case, it's going to be the second observation minus phi times the first observation. But then we also have to subtract theta times the previous guy, and the previous guy is just x1. So when we put all this together, we end up with x2 minus phi plus theta times x1. And we can keep going like this if we really want to. I think I have, I have the actual formula here. So what we get, oh, well, no, that's something slightly different. I'm going to write one more out here just because I think it's interesting and hopefully enlightening to see that if we continue iterating, we're going to get an x3, we're going to subtract our phi x2, and then we're going to subtract theta times the previous noise term, which the previous white noise estimate, prediction, I guess, I never know what to call W tilde, right? Because we're not really estimating white noise. We're not predicting white noise. We're just kind of getting it, I guess. We want to predict X. We don't care about predicting W. Anyway, if we shove all these things together, we're going to get an x3. In this case, we're going to get a minus. Actually, this is probably useful to write out. not just because I like writing out iterations, but because we can see kind of what's happening here. And what's happening here is that we're going to get a plus theta phi plus theta x1. So you can kind of see how this recursion is going to happen. We're going to keep multiplying by theta in this case, which is interesting because in the next line we're going to keep multiplying by phi. So now I'm wondering if we got all that correct. But if we push forward, we can, oh, that's right, of course, this is W. So writing xt in causal form, what we end up with, right? So what we also want to do is we want to understand what the mean squared prediction error is doing. That's going to be important, right? Because that's kind of the variance of our estimate, of our prediction, the variance of our prediction. Well, if we write this ARMA process, this ARMA 1-1 process in causal form, what we get is going to be xt is equal to wt plus the sum I from 1 to infinity of psi I w t minus I. So we already did that. That's just, but the point is that we can actually compute what psi I is. And we can do that, I guess, just using the tools that we had from way back at the beginning of the course when we talked about causal linear processes. In this case, what we're going to do is take I from 1 to infinity, and if we do a little bit of work, we can find that the answer for what psi is should be phi plus theta times phi I minus 1, and then the wt minus I is still sitting here. So what we have now is we have the representation, the causal representation in terms of phi and theta. That's why I was confusing myself with the above thing, because in the above equations, we're looking at W. This is the this is kind of like the invertible setting. And what we're actually doing is multiplying by theta. Whereas down here, we're multiplying by phi. So it just kind of threw me off for a second, and I'm thinking, am I doing this right? No, we're good. We're good. We're in two different settings, causal, invertible. Different ways to represent the process, different coefficients in front of the x's and the white noise terms, respectively. So anyway, what were we trying to do? Oh, yes, we were trying to get the mean squared prediction error. Then the mean squared prediction error, using this notation P capital T, T plus H. Well, we said before, it's going to be a finite summation, J from 0 to H minus 1 of these psi J squared coefficients. Now, when we put this using what we have up above, we know that psi of 0 is going to be 1. That's corresponding to like the 1 that's sitting in front of this guy out here, but isn't really doing anything. So we get a 1. And then we get, well, the phi plus theta squared. And then we get a summation j from 1 to h minus 1 of phi, and now 2j minus 2. Right? Just double checking. That means we would start with, yes, because there's an I minus 1 there. I was trying to make sure that the minus 2 is correct, but yeah, of course, the phi to the minus 1, so it becomes 2. I think I switched I to j, but it becomes 2j to the, or phi to the 2j minus 2. Well, that's a finite geometric series, so we can sum that up. And what we end up with is a 1, a phi plus theta squared, and then we get the sum of a finite geometric series. It's going to look something like 1 minus phi to the 2j minus 2, because again, we're going to h minus 1, so we have to kind of take one step back from the usual geometric series solution. And we get something that looks like that. So hold on. That's supposed to be an h. So we get something that looks like that. And then we say, okay, well, what is this? Well, it's, I guess, the mean squared prediction error. And as we take h to infinity, what happens? Well, this top thing vanishes and we end up with a 1 plus phi plus theta squared divided by 1 minus phi squared, as desired from way back when we talked about this stuff. So again, the idea is that we just end up converging into the variance of the process itself when we take h to infinity. I don't know if there's any interesting intuition here. No, not that I can think of. I think that's more or less the idea. Okay, so again, forecasting, I feel like it's not exactly the most exciting thing to write out, but it is kind of neat. What we learn from all of these equations is that when you're trying to do h step ahead prediction, well, the first thing you need to do is do 1 step, then 2 step, then 3 step, and so on. If you just have an AR piece, it's pretty simple because you just use the previous data points to predict the future data points. If you have a white noise piece, you have to work a little bit harder, and you can work your way up to the white noise as we did here iteratively by starting at time 1 and then going 2, 3, 4, and so on. And you end up with an equation that looks like this. This is just going to be the invertible representation of the data, but we can still use that to estimate or predict white noise, whatever you want to call it. Right, so we're going to talk about one more thing, and then we're going to do some R codes. That's always good. And the last thing I wanted to talk about is the idea of backcasting. Because, okay, we're talking about forecasting, we're using the data set to predict into the future, but we have a finite data set. We could actually predict into the past. So if we want to run time backwards, we could say, hey, if temperatures are going up as we move into the 21st century, well, maybe they'll go down as we move back into the 19th century based on whatever measurements we have. And it is actually a perfectly valid mathematically to consider forecasting in reverse. And it's sometimes, not always, but it's sometimes quite useful. All right, so the goal is to predict h steps backwards in time. All right, so how do we do that? Well, again, what we want is we want a linear estimator. So let me write that out here. We want a linear estimator, and the linear estimator is going to look something like x hat t1 minus h is equal to the sum I from 1 to capital T of alpha I x I. So this is just a general form of a linear estimator. It's a linear combination of my coefficients. Then the question is, what's alpha, right? That's what we want to know. So what we can do is, I'll say as before, we consider multiplying both sides of this equation by, well, xt. What we do is, and then taking an expected value. So we look at this above equation without the hat, and what we say is we say x1 minus h in times xt, and we want to say that is going to be is equal to I from 1 to t of alpha I expected value of xi xt. T. All right, great. Well, that's just a bunch of autocovariances like it always is. This is going to be the autocovariance of T plus H minus 1. And this, on the other hand, is going to be a linear combination, alpha I, of autocovariances of T minus I. Cool. So we have a linear combination of autocovariances, just like we did back when we looked at forecasting for the AR process and forecasting in general. So what do? Well, we write out a system of equations. Therefore, we can get K, the big vector of autocovariances, which is going to run from H all the way down to capital T plus H minus 1. And we're going to have the big matrix gamma. And big matrix gamma is going to be exactly what big matrix gamma always is. It's going to be a big matrix of autocovariances. It's going to be T by T, where we go from 0 to T minus 1. Something that looks like that, right? So this is our big matrix of autocovariances, and we get K is equal to gamma alpha, and solve as before. Meaning that if T is small, we can just invert this thing. If T is not small, we can do one of these iterative methods like Durbin-Watson, which is based on, not Durbin-Watson, Durbin-Levinson, right? There's too many, Durbin did too much. It's in too many things. We can use the algorithm, the Levinson recursion or the Durbin-Levinson algorithm to solve this recursively because we have a Toeplitz matrix, or we could use one of the other methods that we talked about before. Mainly the point is that everything is reversible, and mathematically it's kind of the exact same thing, which is pretty neat. In fact, there is one fun fact to leave you with, which I think, yeah, we have enough time to do. Excellent. So we have one more fun fact, and that is for a stationary Gaussian process, the vector xt plus 1 through x1 is equal in distribution to the vector x. I'm starting it from 0. I'm going to say x. Oh, I see. T plus 1 to 1. I see what I was doing. 0, x1, x, t. Basically, the point is that if I have a Gaussian process, well, first of all, it's stationary. So if I take a vector of data points, I can shift them to the left, I can shift them to the right. It is not going to change anything. But the covariance or the autocovariance is also stationary and it's symmetric. And because it's symmetric, I can flip the order of it and I get the same autocovariance out. And the nice thing about the Gaussian process is if the mean is the same, if the autocovariance is the same, the process is exactly the same, which means that if I have a Gaussian process and I run it forward in time, or if I run it backward in time, it's going to look exactly the same. That's a stationary Gaussian process, just to be precise, because if it's not stationary, then you could run into, well, you're going to run into trouble because the autocovariance may not be symmetric in that way. But if the autocovariance is symmetric like it is for a stationary process, you can flip it around. It looks exactly the same. So I think that's kind of a neat thing to realize. And in the end, when you start looking at this, you realize that actually forecasting for stationary processes is pretty boring because all you're basically doing is using the past few measurements to kind of get a little bit of an idea of where the process is going. But ultimately, the forecast is going to go right to the mean anyway. The interesting bit is sort of in the trend, right? Because ultimately, okay, we want to understand the noise of our, let's say, stock prices or commodity prices or whatever. But in the end, we're going to be looking more at the trend, the non-stationary trend going up, down, or otherwise, rather than just worried about where the noise is going, because the noise is just the noise in the end of the day. But don't take my word for it. Let's jump into RStudio and see how forecasting works on some real data and some simulated data. So we'll do that now. All right, and we're back in RStudio, and now we're going to look at some actual data and look at how to do forecasting in RStudio. So I've already loaded in a couple packages. We have the TSA package, the forecast package, that's a reasonable one to use, and the T-series package. Mainly because I often forget which time series functions lie within each package. So I figure, why don't we just load them all in? Well, I did want to look at this oil price data set, but I'm thinking perhaps the best thing to start with first is to just create some data. So as usual, I'm going to create some white noise. I'm going to create 500 white noise observations. I'm also going to create an AR1. Let's do an AR2 process. It's more interesting. ARMA.sim. And what we're going to need to do is give it a model. I forgot to set a seed so that you get the same answers as I do, or the same randomness as I do. So we're going to start over. Set seed to be 479, course number, go. Okay, and now we're going to generate that white noise, and we're going to generate that AR2 process that I wanted to generate. In this case, we need the model. The model is going to be, well, yeah, that's right. I'm going to need, I believe I need a list. Yeah, a list component with the AR and the MA. Yeah. So my AR piece is going to be, let's say, 0.7, list. So we're going to have 0.7 and let's say 0.2. I think that should be sufficient enough that 1 is no longer a root, because if you plug 1 into the characteristic polynomial, you would get 0.9, I think, or you would get 1 minus 0.9, which is 0.1, which is not 0. So let's hope that we get something that is close to a random walk, but not a random walk. Anyway, what I was supposed to do is say AR is equal to this. And just as a placeholder, I'm going to say MA is empty. Hopefully R doesn't get mad at me for telling it that. And we're going to say, let's generate 500 data points and plot that AR2 process to make sure, yeah, there we go. We get something that's kind of random walky, but not a random walk. It's getting close to being a random walk. If I change the 0.2 to a 0.3, then we have a random walk. Then we're in a little bit of trouble. But we're not there yet. Similarly, why don't I do an MA to process using the exact same 2 coefficients and keeping the AR process empty, so that I can have something that, well, looks like that. So again, MA process is not getting close to a white noise process. It's a whole different thing, so we don't have to worry about that. And keeping with my, I'll call this ARMA 22. And I think I'm just going to use the same coefficient again, but now in both pieces, because why not? Just for consistency's sake. Let's see what that looks like. It should be like a combination of both of them. So yeah, you get like an interesting little random walk-ish behavior. It's not quite, we'll call it a pseudo-random walk because it's not quite a random walk. Though I bet that someone in mathematics has already proposed a pseudo-random walk as some type of probabilistic object, because you just know it has happened. Semi-random walk, pseudo-random walk, quasi-random walk. It's probably all out there in some esoteric articles, but for now we're going to work with these things. All right, so what do we do? Well, I realized that there's actually two things that we want to do. We need to talk about estimation first, and then we need to talk about forecasting, because we did estimation in the last lecture, and I promised that we would actually look into doing estimation for the ARMA process. So how do we do that? Well, there's different ways we can do that. We can use the ARMA function. It's in the TSA library. I believe it should fit to our data. So I give it the data AR2, for example. I tell it an order. So let's give it the correct order, which is 200. Remember, this is ARMA, so the middle number corresponds to the number of difference operators to apply. In this case, I'm saying just do an AR2 model. And let's see what we get. All right, we got something that looks pretty close to the right answer. We got a 0.7, we got a 0.2, 0.23, and an intercept term, because yeah, it has that too. Well, what would happen if I gave it the wrong answer? Let's say I tried to fit an ARMA 2.2 to it. Well, first of all, these coefficients don't look as good. There's a couple things to note. First of all, this coefficient, this AR2 coefficient, is a lot smaller than the standard error that lies below it. So notice that some things have changed here. First of all, the standard error in the correct model is pretty small, right? It's 0.0435, whereas the standard error in the incorrect model is quite high. It's 0.5. I mean, it's quite high in contrast to the coefficients. In 3 cases, I guess in this case it's a little bit lower, but in the 3 cases, the standard error is larger than the actual coefficient itself. That's probably a bad sign. But if we want a better measure, we can always go to, why is the AIC smaller? No, it's not smaller. It's because I can't read numbers. We have 1,413. Over here we have 1,417. So the AIC is in fact bigger for this latter model by 4 units, whatever that means. What it does mean is that by AIC criterion, remember, AIC is model selection. We'd want to pick the model with the smallest AIC. Now, of course, it's not perfect. We might be able to find a model that's very close. Let's try an AR3 process. In this case, we have an AIC that's a little bit closer. It's still bigger by 2 units. In this case, we have an AR3 coefficient, which is basically negligible. It's saying, okay, you wanted a third order AR process. It's not a third order AR process, but I'm just going to give you a coefficient anyway. And the coefficient is almost numerically 0 up to the noise. So these are kind of the things that you would look at and you would say, okay, I think we have an AR2 process. Now, if you don't want to go through all the headache of trying to fit different models yourself, you can use auto ARMA in the forecast package, and it'll just tell you what it likes the best. In this case, it picked AR2, and it gives you the AIC, the AICC, which I honestly forget the formula. It's like a correction to the AIC, probably like a finite sample correct. I'm not sure. I won't speculate. It also gives you the BIC if you prefer fitting with respect to that. There's no right answer for fitting one versus the other. Some people, I think, in certain cases, like AIC or BIC over the other. But yeah, I don't think there's a strong case that you should be using one or the other here, but maybe there's an article out there or a Stack Exchange post that says otherwise that I'm not familiar with. Anyway, well, why don't we try the same thing? We can use auto ARMA on our MA2, and it didn't quite get the right answer. That's quite interesting. See what it did? It got the MA pieces here. First of all, they have a negative sign. And second of all, the AR piece, there's an AR piece in here, and it actually looks like it has some significance to it in the sense that it's just a big number with respect to the standard error. Remember, we can kind of look at the estimate with respect to the standard error to tell how significant, in some sense, our coefficients are. But that's quite interesting. I like it when that happens because it means we can fit the correct model using the ARMA process or the ARMA function and try to see if we actually get what we get. Presumably, we're going to get a larger AIC or BIC or whatever it's using. Yeah, we get a much bigger, or no, we get smaller. Okay, so why did it do that? Well, let's try this model. And that's interesting. It's doing something different. I see what I did wrong. I missed one key thing that was going on here in AutoArima. It didn't fit an ARMA 1.2 model. It fit an ARMA 1.1.2, so it actually included a first difference. That's quite interesting. So it decided that it would rather have a first difference in here. So let's compare those two now. Yeah, what we would have is we would have this model, which is MA. This would be the correct model, which is getting coefficients pretty close to the ones that I selected. Where'd my mouse go? But what it tried to fit was an ARIMA model with an AR1, an I or D value of 1, a first difference, and then a 2. And for some reason in this case, I'm getting I got an AIC of 1410 and an AIC of 1413 here, which is quite peculiar because I think up here in AutoArima, it seems that what we got was an AIC of 1415, even though the coefficients are fitted look about the same. It's quite interesting. This is a bit of a peculiarity. What I'm wondering is if the two fitting methods are using different criterion. So let's see what this one is doing. Now we're just kind of investigating on the fly. I like this. So, right, there's an estimation method that you can set. And in this case, it's not going to tell us what different estimation methods we can use. Great. I think up above it says something like there's a CSS ML, an ML, and a CSS. Off the top of my head, I'm not sure what it's referring to, except that ML is most likely maximum likelihood. Meanwhile, in a separate R package, you have auto.arima. And auto.arima, yeah, is going to select based on AIC. And I mean, yeah, the method is maximum. CSS is conditional sum of squares. That makes sense. The fitting method, maximum likelihood or minimize conditional sum of squares. The default, it's not really a sentence, but that's okay. The default is to use conditional sum of squares to find the starting value, then maximum likelihood. So presumably they seem like they should be doing the same thing, but they're giving me different answers, which is quite interesting. At the very least, I think this is also good evidence that the AutoArima function is very useful because it's going to try a bunch of different models, but it is good to try some yourself. The reason is that if we forget about AutoArima for a second, if we just look at these models, we might get AICs that are very close to each other, or BICs that are very close to each other. And it just means that just because one is slightly smaller or slightly greater than the other doesn't mean that we have to choose the one that has the smallest AIC. If the two AICs are extremely close to each other, it means that these models in some sense are extremely close to each other. So ultimately, you could almost pick either, and you might want to look at both of those models and try to see how they represent the data. Because ultimately, if you're trying to use the models to fit to the data, a lot of these models are going to give you very similar residuals, so they might still have a very nice fit, mainly because any coefficients that shouldn't be there are kind of set to 0. And if you do a first difference of a process, then you often end up getting just a different time series process with different coefficients that you can estimate. So again, these are all little things to be aware of when you're doing estimation. Oh yeah, we never did our estimation for our ARMA 2.2. So let's try that just to see what happens. We'll start with auto ARMA just to see. And auto ARMA, once again, no, it gave me, I was worried it was going to give me the exact same coefficients as before. It gave me different coefficients than the last time, but in this case, it gave me still a 112. So it didn't quite get what we wanted. It's interesting that it seems to really like that model. It really likes taking a first difference. So if I take my ARMA 2.2 and I plug in, again, the right answer that I know because I generated this data, well, what we end up with is, well, oh, you know what it is? I bet it's the intercept term. I'm betting that it's the fact that the auto ARMA is not fitting. I believe it's not fitting an intercept term, and that's probably why it's doing that. I don't see. I'm going to take a guess and say that's the difference, because for some reason we seem to be missing that in this case. Anyway, if we were to try something different, like an ARMA 112 process, we should get something that has a larger AIC value here. So I think that's the downfall of auto ARMA is going to be my guess. Hopefully, since this is recorded and you can watch this if I say something wrong and forever and ever, but hopefully that's not the case. Also, I did want to note in this case, it's not clear that the AR2 piece should actually be there. We know it should be there because that's how we generated the data. But if we go back to fitting the correct model, what we see is a very small AR2 coefficient, especially when you look at the large standard error that's associated with it. So if I were looking at this data and I didn't know what the right answer was, I might think to myself, well, maybe I should fit an AR1 MA2 process. And hey, now there's an interesting result. We actually get a smaller AIC with this model. So again, it's not the model that we wanted, but it is giving us a smaller AIC based on the data. So it's one of these things, right? Time series is a very exploratory subject. You have to just try a lot of different models and get a sense of what's going on. Look at the AIC, look at the estimated coefficients, look at the variance, the standard errors, all of these things to try to get an idea about what's going on with your data, right? All right. But we're not done yet. We still need to do some forecasting. So what we should do is we should actually, no, it's funny. I think we can even do forecast, compare two forecast methods to each other, but I didn't actually prepare that, but we can try it anyway. So we're going to call this, well, we'll call model 1, the one that I wanted to fit. And then we'll call model 2, let's say this one. So we have two different models. Our process, if we plot it again, the ARMA data is going to look like that. So it's kind of jagged and noisy. It almost looks like there might be something seasonal going on here, but there isn't. And the fact that it kind of fluctuates up and down and up and down. Now, what were we going to do? We're going to use forecast in the forecast package. So it's always nice when a package has a function that has the same name as the package itself. But it's a very easy to use function. It basically says, got to keep my voice going for just a little longer. It basically says we give it a object, and we tell it how far to fit into the future. And then it's going to just tell us some stuff about it. So if we go all the way down here, are they going to give us an example? Yeah, in this case, they use ETS to fit. It's a different way, different thing for fitting. We'll talk. But then what they do here is, yeah, they basically say, yep, use forecast, and I believe you can use H or it's number of periods of forecasting. So let's try that. And I believe it should give us a nice plot. ARMA 2, and we're going to say H is equal to, I don't know, 20. Oh, I didn't plot it. I thought it, let's see if this works. Yeah, that's what I was looking for. I have to tell it to actually plot my forecast. So let's try to zoom in here. So let's see, we need X from, or XLim from about, say, whatever, 490 to 520. And the Y limit, it looks like it's going to be between, let's say, plus and minus 5. So let's try and zero in on that. And it got mad at me because I was supposed to put a comma here and not a colon. So there we go. There's our beautiful forecast, right? We have our data, it's jumping around, and then it stops here. And it says, okay, how are we going to forecast? Well, we're going to start tending towards the mean ever so slowly. The big cone is giving a sense of the variance, or the mean squared prediction error, I should say. And as you can see, if we go back to the plot that I didn't zoom in on, it, in fact, spreads out pretty fast. We can go really far into the future, but again, it's not the most interesting thing to look at because effectively the prediction goes right to the mean and then it just spreads out. If we go back to the plot, we're looking at 80% confidence, I guess, prediction interval and a 95% prediction interval. So yeah, it's quite wide. I mean, there is a lot of variance in the data. If we try doing this for the MA, which one, 2, let's see. Yeah, it still does spread out quite rapidly. But yeah, there's not a lot. Like I said, forecasting in this case is not the most exciting thing. Now, yeah, I think we still got a few minutes, so I'm just going to run even further off script than I already have. Because I know there's a way, I think, yeah, accuracy is what I wanted to find. Oh, good. Luckily, it started with an A. I couldn't remember what the function was I wanted. So this returns a range of summary measures of forecast accuracy, because when you're picking a time series model, right, you don't just want to, you can consider the coefficients, you can consider the AIC or the BIC, you can also consider the forecast accuracy. It's kind of like, it's almost like a, I don't want to say, I was thinking like a leave one out prediction type thing where you try to predict based on your model. But in this case, you just use the data going forward in time to predict the next guy. And what we get is, well, a couple different things. So I think what we should be able to do is plug in our, we should be able to plug in our model like MD1, which was the model fit with the ARMA 2, and we should be able to give it our data, which is ARMA 2, I think. And what is it doing wrong? With the model itself, and the model object should have everything within it. Why do you give me a bunch of nans? Rough. It's just not working today, right? All right, and we're back after a couple R technical difficulties, as you can see by all of these warning messages. So I ran into a problem. That is, I fit my models using the ARMA function, lowercase a, in the TSA package, but the accuracy function is in the forecast package where there is an ARMA function with a capital A. So what I was supposed to do was load in the forecast package, and then instead of fitting my models with a lowercase a ARMA, I'm supposed to fit them with a capital A ARMA. So good job, R. But anyway, yeah, we can do that. And as you can see here in the forecast package, there is another method for fitting ARMA. It is a wrapper for the one that's in the stats package, because of course the stats package also has a function called ARMA that you can use to fit ARMA models. But the important thing is that by fitting, basically by using capital A ARMA to fit the model, then what I can do is I can, well, look at the summary, which is going to give me all the prediction errors that I wanted, but it's also going to give me a lot of other stuff that's going to get in the way. So what I want to do is I want to go back and try what I was trying before and look at the accuracy. So here, let's slide this over so we can maybe stare at it on one line. Is it going to give me one line? There we go. So at the bottom of the screen here, what we have is the training accuracy of Model 1, and this is with respect to many different criteria. For example, this I think is the mean error, the root mean squared error, the mean absolute error, can I get them all right? The mean prediction error, the mean absolute prediction error, the mean absolute squared error, and I'm not sure what ACF1 is, but I wouldn't be surprised if it has something to do with the autocorrelation. Let's see. MPE is mean percentage error. I was close. An absolute mean percentage error, mean absolute scaled error, and the autocorrelation of the errors. Okay, so the point is there's tons of different forecasting accuracy measurements. So if you were already upset that you had to decide between AIC and BIC, well, now you've got a ton of different measurements, all for saying how accurate is your forecasting, using lots of different values here. What we can do is we can also look at this for our two different models. And in fact, why don't we try this? See if R is going to be, how many times did the correct model give me a better accuracy than the model that was chosen as a better fit for our data? And in all of them, it failed except the root mean squared error. So yeah, basically, if we remember what we did before, Model 1, MD1, is the ARMA 2.2 model from above. So that's how I generated this data as an ARMA 2.2 model. But if you notice, the AIC is bigger than an ARMA 1.2 model, where the AIC is slightly smaller. We also notice here that the standard error for my coefficients in the ARMA 1.2 is actually better than, is smaller in the sense what I mean by better, than the standard errors in this model above. So in some sense, even though the data I know I generated as an ARMA 2.2 model, it seems that the ARMA 1.2 better fits this finite sample of data. And that's okay, because actually in most of the measurements, it's giving us a better prediction error, except of course in the root mean squared case where the Model 1 is actually doing better than Model 2. So yeah, but if you also notice in the root mean squared case, they are almost numerically the same. We have a 96322 and a 96328. So, okay, technically Model 1 is doing better, but it's in the, fifth decimal place. So it's basically equivalent statistically. Actually, looking at most of these, we notice that the prediction errors are almost identical in many cases. And that's a good thing to note, because it's kind of saying that, okay, I can pick one model, I can pick another model, but ultimately we're getting about the same thing in each case. So we shouldn't worry too much about it in some sense, though overall it seems that this Model 2 is actually preferable to Model 1. All right, so given all of that, well, maybe we should look at some real data. So as I was going to start this section of the lecture, there is an oil price. Of course, it's not auto-completing now. Oil. Man, R is just not cooperating on a night like tonight. Anyway, we have this oil price data. I think I have to say data oil.price to make it come out. And then I can say plot oil.price. And we have something that, wow, looks like that, because something must have happened around 2001 that drove the price of oil up really high. Anyway, what I don't want to do is I don't want to deal with that giant spike. So I think what we will do is look at our data set. I think this is monthly, so let's truncate this. All right, so we've got 241 measurements. Oh, I guess that's, 20 years worth or so. So let's try plotting the first 10 years or so. Yeah, of course it's, I'm just going to call it oil. Mainly because now what we can do is we have something that's not going to massively shoot off, into the sky as we go forward. We do have a big spike there. It's actually quite interesting. The big spike right around, I guess, 91 or 92. I'm wondering what that would have been. Was that the, no, the Gulf War was 89? I forget. Anyway, there was a spike there. It looks like around 91 or 92. Anyway, we can use the methods that we looked at before on this data set. So we can use auto ARMA to try to fit an ARMA model, and it comes up with an MA1 after a first difference, it should say, which is quite interesting. It makes me think that maybe the process looks non-stationary if you were to fit a ARMA model to it. So I'm going to fit ARMA, but I'm going to make sure that I use capital A so that we can look at the forecast accuracy. And the order I'm going to fit is going to be, well, the same one as before. And in this case, we get that one. I'm going to say MD oil.md1. But we could also try some other models just to see what they look like. So what happens if we don't take a first difference of our process? Well, now we get an MA piece really, really close to 1, and that's telling us that this process is almost non-invertible. That's bad. We want it to be invertible. Probably similarly if we do an AR1. No, that one actually didn't give us something that's completely non-invertible. So that one actually didn't do so badly. I mean, it did give us a higher AIC, I should say, than this model, but it did do much better than no, it gave us a lower AIC. What am I saying? It's something about looking at these numbers is just tricky. So actually in this case, this is quite interesting. The ARMA model, the ARMA 1 or the ARMA 1-1 with the first difference being 0 gave us a smaller AIC. Again, I suspect it's because auto ARMA probably has something to do with the non-zero mean that needs to be accounted for. But I'm going to try just to fit a couple more models just to see what happens. The ARMA 2-1 model seems to give me an AIC that is nearly identical. It is ever so slightly smaller, to the point that they're probably about, in fact, in the BIC in this case is actually bigger, right? There's a lot of ambiguities, right? You never know exactly what the right answer is. We could try an ARMA 1-2. That also gives me a bigger AIC and BIC. So let's stick with ARMA 1-1. I kind of like that model personally. And we'll just call this oil.model, I guess 2, because I already fit model 1, but model, that was not as good of a model, I think. All right, so now we have oil.model 2, and we can look at things. We can look at the forecast accuracy of this one. And yeah, we get some values. Again, they're not the most intelligible values. They're really meant more for comparison purposes. But if we look at this model 1, we do see that the forecast accuracy is bigger. It's interesting with the percentagers like that. In these cases, yeah, it looks like overall model 2 is doing better than model 1. So the ARMA 1.1 is actually not so bad for this case. And lastly, if we really wanted to, we could forecast with our oil and say H is equal to maybe 20 and see, of course, I forgot to plot it. So it's just going to spit out a bunch of values. Yep, so once again, it basically just lays constant at the mean. And you can see that actually if we just stare at the values that are spit out at me, it's basically the forecast is 19.02 on to infinity. It didn't even really fluctuate at all in this case. We have the low and the high at 80 and 95% confidence. In which case they do start to expand quite a lot, though they probably weren't going to predict the giant spike that happened once we crossed into the 21st century. Regardless, this is a lot, I know, of different things to do, but see, I worry a bit that it feels a little bit messy, but in some sense, this is kind of, time series is a bit of a messy subject, because ultimately what you're going to be doing is you're going to be trying different models. You're going to be using AIC, you're going to be using BIC, you're going to be using forecast accuracy. You're going to look at the estimated coefficients. You're going to stare at it, maybe try a first difference, test for stationarity. We didn't actually do that in this case. We could do that, but the fact that we have a fairly nice fitting ARMA model without a first difference makes me think that it's probably not or we don't have to worry about stationarity, at least in this case. But these are all things that we have to consider when we look at time series data. It's a very exploratory subject. It's a lot of fun. There's no real right answer in some sense. You just kind of have to work your way through it and see what you get. So yeah, with that, there's something else that we haven't discussed yet for ARMA models, and that's seasonal ARMA models, because very, very often you're going to see seasonal fluctuations in your data. We don't see any here, but if we recall that prescription drug data set, which I specifically didn't choose for this example because it has a seasonal component, that's something that we want to model, and that's something that we will model, but we're going to do it in the next lecture. So see you there.